this chapter is those two major topics: magnetic force on moving charges and current carrying wires. So we have this equation, F equals QV crossed into B. So this gives you if I already know the magnetic field in a certain space, then it tells you the force experienced by a charge is equal to the cross product of the velocity of that charge and the magnetic field. So compare this for electricity, we would compare this to this equation, F equals QE. For the electrical force, a charge does not need to be moving in order to experience a force. It could be just stationary, right? And then as soon as I turn on an electrical field, that charge will experience a force. And if it's positive, the force that it will experience will be in the same direction as the electrical field, right? And if it's a negative charge, it will experience a force to the left. But this one is saying, okay, if there is a charge, and if I turn on a magnetic field, B is the symbol for magnetic field. If I turn on the magnetic field, then that charge will experience no force, right? It has to have a velocity to experience a force. Not only does it have to have a velocity, it has to have a particular kind of velocity. So it's not sufficient for it to have, let's say if its velocity is like this, right, it still won't experience a force. So the cross product of its velocity and the magnetic field has to be non-zero in order for it to experience a force. So if the charge is moving either this way, if I turn on the magnetic field, it's going to experience no force. So that means it's just going to continue moving in that direction. If it's moving in that direction, then it will also experience no force, right? The cross product, remember, is the magnitude of the V, the magnitude of the B, times the sine of the angle between the V and the B. So in this case, if the angle is 0, sine of 0 is going to be 1. And then sine of 180, right? If the charge is moving the opposite direction, so sine of 180 is also, sine of 0 is 0.
0.
Yeah, and then sine of 180 is also 0. So that means that the force experienced by that charge is 0. The maximum force will be experienced by the charge when the angle is 90. Then if the charge is moving this way, then that will be the maximum force experienced by that charge, or this way. You see. So, so we could say to maximize the force, to maximize F, make the theta 90 or 270, right? And then the maximum force will occur. So maybe you could say this is 90, and then this is 270. You see, so then that provides the maximum force. So if it is 90 or 270, what's going to be the force? So let's see if this is Q, B is like this, and then B is like that. You see, so now take the cross product between V and B. So you do your 4 fingers in the direction of V, right? Then curl them in the direction of B, and your thumb points into the board. You see, V crossed into B, V crossed into B, into the board. So the force is into the board. But that's if the charge is positive. If the charge is negative, then you switch that to out of the board. So everything I'm going to say relies on the charge being positive, and when the charge is negative, it switches. Just like here, if the charge is stationary, it experiences a force this way. Well, it doesn't matter whether the charge is stationary or not. For electrical field, the force experienced by the charge is always in the direction of the E, but that's, of course, assuming that the Q is positive. If the Q is negative, then the force is switched to the left. You can see. So to maximize F, okay, so the force is into the board. So then if the opposite is true, if the charge is moving down this way, I guess we could say that's angle of 270, then you say your forefingers in the direction of the V, crossed into B, the thumb is up. So the force is out of the board. So you see here, forefingers in the direction of the V, crossed into B, down, you see, your thumb. And then here, V crossed into B, up. So then what's the resulting path of that charge? What's the resulting path? So if the charge comes in moving at 90, okay, so let's say it's this way, right? So if it's moving this way, we said that the force is into the board. So then it's going to go like this, into the board like this. Imagine we're a 3D, so it's going to go like this, into the board, then come out. It actually ends up being a circle, you see, like that. That's if it was moving like this, you see. If it's moving down like that, then the charge is going to come like this, and the force is what? Out of the board. So it's going to go like this toward you, then it's going to go like this. You see, whereas the other one is going to go like this into the board. You see, into the board, like that, into the board. Then the other one is out of the board, gets closer to you, out of the board. You see, so it becomes a circle. Go up here and say the units of magnetic field. So this is newtons, this is coulombs, and this is meters per second. And then the units of the magnetic field is called a Tesla, named after Nikola Tesla, right? So Tesla is a common name these days because of the car. But before that, probably a lot of people didn't really know about him that much. But the physics world is very famous, though. So Newton, so we could say the Tesla is the metric unit of the magnetic field, and it's equivalent to a Newton second, Newton times second, right, over a Coulomb meter, Coulomb meter. Yeah, but Newton per Coulomb is units of electrical field. So that's this is units of electric field, and then meters per second is units of velocity. So basically, you can kind of say that Tesla has units of electrical field, which is this guy, and then divided by velocity. Well, you see F over Q is the electrical field, and then you have, this is velocity, so you can kind of say, yeah, that works that way. You can also say Newton per Coulomb is equivalent to a volt per meter. So then you could say volt times second over a meter squared, although it doesn't really take you anything that useful. Yeah, it doesn't really, it just kind of dead ends right there. Okay, so that's the units of the Tesla, but one Tesla is actually a very, very huge magnetic field. The typical magnetic fields experienced on Earth, like the Earth's magnetic field, are Gausses. So we use the Gauss for more realistic magnetic field. 10,000 Gauss is 1 Tesla. 10,000 Gauss is 1 Tesla. So 10 to the 4th Gauss. So those are more realistic magnetic fields. Let's see here. Oh, just a second. Okay, just a second, everyone.
I gave you something in the beginning.
Yeah, 25 to 65 micro Tesla, right? 25 to 65 micro Tesla, which is 0.25 to 0.65 Gauss, right? So 0.25 to 0.65 Gauss. So you can kind of see here, remember that 10 to the 4th Gauss is 1 Tesla. So this would be, micro Tesla would be 10 to the minus 6 Tesla, all right? So then you could go back 2 spaces and make this into a 10 to the minus 4 Tesla, and then use the fact that 10 to the 4th Gauss is 1 Tesla, get rid of this and call this a quarter of a Gauss. So this would be the weakest magnetic field on Earth, about a quarter of Gauss to the strongest. The weakest magnetic field is going to be around the equator, right? And then the strongest magnetic field are going to be where the poles are, where the north and south magnetic poles. So the Earth looks like this, with one giant magnet in the center. The north magnetic pole is where the south, near the south pole, and the south magnetic pole is where the north pole is. And the magnetic field lines come out of the Earth like this, and then they go into the south. So the strongest magnetic fields is the strongest concentration down here and up there. So we would expect that to be the 0.65 Gauss, right? And then the weakest magnetic field, kind of near the equator, right here, those would be about a quarter Gauss. So in LA, it's probably a little bit bigger than 0.25. Let me see here. Magnetic field in Los Angeles. Okay, these are the components of the magnetic field, 24. And these are probably in units of, let's see here, the total magnitude of the magnetic field vector. Part of the reason that I also show you guys this is all of you, I want you to be able to be an independent scientist. Go to any website, look at numbers, not be afraid of them, be able to interpret anything. So here, the total magnitude of the magnetic field vector is about 0.5 Gauss units, or equivalent to 50,000 nanoteslas. To find the components of the magnetic field anywhere, visit the standard magnetic field model and enter the date and your geographic latitude. The table below shows the representative components for June 1. So it always changes. Depending on the date, the magnetic field is fluctuating. And remember, it's going to eventually reverse. The magnetic field will reverse, it will weaken, and it will reverse every like 300,000 years. The magnetic field reverses. So right now it says this is as of June 1, 1999. So 24,000 nanoteslas, right? So for Los Angeles, let's see here. I'm trying to fit it into this page. So for Los Angeles, we have BX 24,276, BY 5996, BZ is equal to 41,636. Right? So what do we see here? What's the total magnetic field? The Z magnetic field in the Z direction is the component of the magnetic field that's going into the board. You see here? I mean, into the ground. You see here, the component, you see how this is dipping down? This is called the dipping angle. So the magnetic field Z is the component of the magnetic field going into the ground. We usually don't measure that. We do the BX and the BY. Compasses work by measuring the BX and the BY, but they usually don't measure BZ. BZ is the component going into the ground. So the total magnetic field at Los Angeles is this squared plus this squared plus this squared square root. You guys see that? This squared, this squared, this squared, square root. That gives you the 48,568. So this is the total field. It's square root of bx squared plus by squared plus bz squared. Okay, and then that gives you the total B. So in terms of this, what would that be? This is nanoteslas. So then you go 1, 2, 3, 4, 5. See, this is 10 to the minus 9. When you go back 5 spaces, that makes this 10 to the minus 4. And then you can call this a Gauss. Right? Gauss. So then that's roughly around 0.49 Gauss in LA. You see, that's stronger than it's at the equator. At the equator, it's a quarter Gauss. You see, so because LA is above the equator, the magnetic field is getting stronger and stronger. It should be getting stronger, and the Z component should be getting bigger because you see how it's starting to go into the ground. By the time you get to the north, by the time you get to the south magnetic pole, it should be going into the ground. So the Z component should be very, very strong. So if we go to, let's say, New York, what's going to happen? You see New York, the X component is smaller, the Y component is smaller, but look how strong the Z component is. Do you see? And so it's going into the ground more. And then what's the total B? 0.54. 0.54 Gauss. So yep, it is getting stronger.
I have a question.
Yeah.
When we're trying to think about the X and the Y direction, would X be from pole to pole and Y would be around the Earth, or vice versa?
Well, I'm not sure how they're defining the BX and the BY, but it could be that X is, let's say, north, let's say X is east-west, and Y component might be north-south component. Okay. And then the Z is into the ground, out of the ground. Yeah. So, so generally, as we're going towards northern cities like San Francisco, the Z component should be getting larger, and the total B should be getting larger. Okay, yeah, that makes sense. Yeah, it seems like it works. Okay, cool. So a little bit about, it's nice to know a little bit about the field. Magnetic field of planets. Jupiter's magnetic field is huge. Oh, magnetic moment is something that I'll tell a little later. Magnetic field strength, 4.170 Gauss. So that's probably an average value they're taking, but you see, it's not a Tesla, of course, but that's still compared to Earth, that's still very, very strong. The Earth, the biggest it gets is 0.65 Gauss, right? So this is 4 Gauss, and that's the average value. So you can see how strong that is. Very, very strong. That would make it around 8 times stronger than the Earth, right? Because ours is half a Gauss on the average. Yeah, it's about 7, 8 times stronger than the Earth's field. How about the sun? You probably know, Joy. Let's see.
That's funny.
Yeah, that's your specialty. How the sun's magnetic field works. A sun's magnetic field flips every 11 years, right?
Yes.
Whereas the Earth is like sun's magnetic field strength, Tesla. Okay, let's see. Sun's magnetic field strength are as large as 0.3 Tesla. See, it's still not even a Tesla. 0.3 Tesla, 3,000 Gauss. But of course, that's a lot stronger than that's a lot stronger than even Jupiter's was what? 4 Gauss? Yeah, 4 Gauss. That's a lot stronger. 3,000 Gauss is like kills that. Okay. How about let's put something like this: magnetic field strength of different magnets.
Professor, is it true that I know people use that 1 Tesla is similar to that of a bowling ball falling on top of your head, 6 feet above?
Oh, is there like general? I haven't heard that one. The
Yeah.
pain that it would cause, you mean, or what?
Yeah, it's like a 6 pound bowling ball. The force it would hit you with is equivalent to 1 Tesla.
Oh, well, I'm not sure because Tesla is not really a unit of force. But you're saying if you had a magnet that would at 1 Tesla, it could
Uh,
cause that much harm to you?
yeah, something like that. I guess I don't
Oh,
remember too well.
I would have to see how that's worded. Yeah.
I'll see if I can find it. It's
Yeah,
just good to see how strong it is.
yeah, exactly. Oh, let's see. Are there different strengths of magnets? What cause different strengths of magnets? What are 4 types of magnets? Magnetism is a very interesting phenomenon, and we all, as kids, have always wondered about it. So it's kind of nice to learn all these things. Neodymium iron boron magnets, samarium cobalt, alnico, temporary magnets. So let's see here. Oh, okay. So here is some kind of comparison. Gauss measurements in comparison. Half a Gauss, Earth's magnetic field, you see. Then you have 100 Gauss, typical refrigerator magnet. Remember, Jupiter was 4 Gauss. So a typical refrigerator magnet, that means, is even stronger than Jupiter's magnetic field. The sun's magnetic field was 3,000 Gauss. So keep that in mind. Magnetic rubber grade Y. Ferrite ceramic magnets, 3,000 Gauss. So that's about the sun's magnetic field right there. Ferrite ceramic magnets, 11,000 Gauss. So now we're talking in Teslas, what would that be? Remember, 10,000 Gauss is 1 Tesla. So this is already slightly more than a Tesla. Let's see, samarium cobalt grade 2. 12,000 Gauss, alnico grade 5. So we're talking slightly more than a Tesla here. 13,000 Gauss, neodymium grade 4. I think those are the strongest. 13,000 Gauss. $13,000 magnets. 13,000 Gauss. Does CAT scans use magnetic field? CAT scans versus MRI differences. CAT scans use radiation, X-rays, and MRIs do not. MRIs provide more detailed information about the inner organs, such as the brain, skeletal system, reproductive system, and other organs that is provided by a CAT scan. CAT scans are quick, painless, and non-invasive. MRI scans are not invasive, but they are noisy, take more time. MRI scans are costlier than CT scans. MRI scanners may cause a safety issue due to its strong magnets. Also, the MRIs use a strong, I guess CT scans don't use magnets. They use radiation. CT, computerized tomography scan, is a combination of a series of X-ray images taken at different angles. The CT uses a computer to create images from these X-rays. So it uses an X-ray. MRI is a scan that uses magnetic fields and radio waves to produce a detailed image of the body's soft tissues and bones. Wow, I love those two technologies, just brilliant. Both of them invented by physicists. CT, computerized tomography. So MRI uses magnetic fields. So let's see, the magnetic field lines, MRIs use and send superconducting magnet and radio frequency waves into the body. The magnetic field lines up atoms either in a north or south position with a few atoms that are unmatched, keep spinning in a normal fashion. When a radio frequency is added, the unmatched atoms spin in an opposite direction, and when the radio frequency is turned off, those unmatched atoms return to their normal position, emitting energy. The energy emitted sends a signal to the computer, and the computer uses mathematical formulas to convert the signal into an image. You guys see that? I mean, God, a brilliant idea. So this magnetic field, very strong magnetic field, lines up all the atoms except for a few. And then the radio waves flip those few of them, and depending on the energy they emit, that sends a signal to make that into an image. I'm just trying to see here the strength of the MRI. Let's see here. See, one thing led to another, led to another, led to another. We were just going to cover the units of magnetism then, but that's what happens when curiosity peaks. That's how science works, right? Magnetic field strength in MRI. MRI scanners come in different field strength, usually between 0.5 and 1.5 Teslas. That is strong, you see. Remember the strength of the magnets we saw? Niobidium was what, 13,000 Gauss? Well, this is even stronger than that, 1.5 Tesla. What is that? That's 15,000 Gauss. Yeah, so I mean, we're talking strong magnetic field. 0.5 to 1.5 Tesla. When additional energy in the form of radio wave is added to the magnetic field, the magnetic vector is deflected. Oof, wow. That's why you take off everything when you have an MRI.